March 12, 1915, Toulon Naval Arsenal, southern France, 9:47 p.m. The French artillery officer stopped counting at Rat Corps 17, overwhelmed by the sheer number of dead animals scattered across the concrete test chamber. Captain Henri Moulard, assigned to the Ministry of War's Experimental Weapons Division and deeply skeptical of civilian scientists proposing miracle weapons, stood behind reinforced glass watching what military historians would later dismiss as pseudoscience, but which represented humanity's first successful attempt to weaponize sound itself. 50 feet away, behind steel baffles designed to protect operators, Dr. Robert Williams Wood's apparatus hummed at frequencies below human hearing, generating pressure waves that had killed every living thing in the target chamber within 90 seconds of activation. What Moulard didn't know was that he was witnessing the culmination of a 2-decade obsession with acoustic physics that had consumed not just one brilliant American physicist, but dozens of researchers across Europe and America, all pursuing the same terrifying possibility: that sound, properly focused and amplified, could kill as effectively as bullets or shells. The sonic weapon, a concept that sounded like a fantasy from Jules Verne novels, but between 1900 and 1945, some of the most respected physicists in the world, men who would later win Nobel Prizes and reshape modern science, staked their reputations on proving that acoustic energy could be weaponized. And for a few horrifying minutes in laboratories in France, Germany, and later the United States, it actually worked. The story begins not with weapons research, but with a Harvard physicist studying the physics of ultrasonic frequencies and stumbling onto something that shouldn't have been possible. 1899, Johns Hopkins University, Baltimore, Maryland. Robert Williams Wood, a 29-year-old experimental physicist with a reputation for unconventional research and theatrical demonstrations, was investigating the properties of high-frequency sound waves, frequencies above the range of human hearing, beyond 20,000 cycles per second. Wood had discovered that ultrasonic frequencies exhibited bizarre properties. They traveled in straight lines like light rays rather than spreading in all directions. They could be focused using parabolic reflectors, and they carried far more energy than audible sound at equivalent amplitudes. During experiments measuring ultrasonic reflection, Wood noticed something disturbing. Laboratory mice housed near his ultrasonic generators died with no visible signs of injury. Dissection revealed internal hemorrhaging, ruptured organs, and tissue damage consistent with violent mechanical trauma. But the animals showed no external wounds. Wood initially attributed the deaths to equipment malfunction, perhaps electrical discharge or chemical exposure from the apparatus. But repeated testing confirmed the pattern. Exposure to high-intensity ultrasonic waves killed small animals through internal damage while leaving external surfaces unmarked. Wood understood the mechanism immediately. Sound waves were pressure variations propagating through air. At sufficient intensity, these pressure variations became physical force, compression and rarefaction cycles that could disrupt tissue, burst cells, and damage organs. Audible sound at such intensities would be unbearably loud, causing immediate pain and hearing damage before reaching lethal levels. But ultrasonic frequencies, inaudible to humans, could potentially reach lethal intensities without warning. The implications were disturbing enough that Wood initially didn't publish his findings. A weapon that killed invisibly, silently, and without physical projectiles contradicted fundamental assumptions about warfare. Guns and artillery were visible, audible, and comprehensible. A sonic weapon would be none of these things. But Wood's reluctance to publicize his research didn't prevent others from pursuing similar discoveries. By 1905, acoustic weapon research was underway in Germany, Britain, and France. European military establishments, observing rapid advances in physics and chemistry, funded exploratory research into potential military applications. Wireless telegraphy had proven that invisible electromagnetic waves could carry information across vast distances. X-rays had revealed that invisible radiation could penetrate solid matter. Military researchers wondered, could other forms of invisible energy be weaponized? Professor Raoul Pierre Pictet, a Swiss physicist working in Berlin, independently discovered that focused ultrasonic waves caused tissue damage. Pictet's approach was more systematic than Wood's accidental discovery. He designed parabolic reflectors that concentrated ultrasonic energy into narrow beams, achieving intensities far higher than unfocused sources. Tests against animal subjects confirmed lethality at ranges up to 10 meters. Pictet submitted proposals to German military authorities for developing acoustic weapons that could disable enemy soldiers without ammunition or visible effects. German military engineers were intrigued but skeptical. Pictet's ultrasonic generators required enormous electrical power, kilowatts per second, to produce lethal effects at modest ranges. The equipment was bulky, fragile, and required line of sight to targets. Compared to machine guns or artillery, the acoustic weapons seemed impractical, but the potential for invisible, silent killing justified continued research. By 1910, German military laboratories had constructed experimental sonic weapons, testing them against animals and, disturbingly, against cadavers to assess effects on human tissue. British researchers pursued parallel investigations. Dr. Alexander Graham Bell, famous for inventing the telephone, had spent decades studying acoustic physics. In 1911, Bell and his research partner, Charles Sumner Tainter, experimented with high-powered ultrasonic transducers capable of generating focused acoustic beams. Bell recognized the military potential immediately, but was morally opposed to weapons development. He shared his findings with the British War Office while advocating against weaponization, hoping scientific transparency would prevent the development of acoustic weapons by discouraging secrecy. The strategy backfired. Bell's warnings convinced British military authorities that acoustic weapons were feasible, accelerating rather than deterring research. Then, in 1914, the Great War began, and academic curiosity became military necessity. The Western Front devolved into static trench warfare within months. Machine guns, artillery, and barbed wire created defensive positions that conventional infantry assaults couldn't breach without catastrophic casualties. Military authorities desperately sought technological solutions: poison gas, tanks, aircraft, anything that might break the stalemate. Acoustic weapons, despite their experimental status, received renewed attention. Dr. Robert Wood, now an established professor at Johns Hopkins, was approached by French military representatives in late 1914. France faced imminent defeat if the war continued unchanged. Any technology offering a tactical advantage warrants investigation. Wood initially refused, citing ethical concerns about developing weapons, but reports of German chemical weapon development, chlorine gas attacks were rumored but not yet deployed, convinced Wood that Allied forces needed every possible defensive and offensive capability. Wood agreed to develop an acoustic weapon for French military testing. His design philosophy was pragmatic. Rather than pursuing high-frequency ultrasonic weapons requiring complex generators, Wood proposed using infrasonic frequencies, below human hearing, typically 1 to 20 cycles per second. Infrasonic waves were easier to generate using mechanical oscillators, carried farther through air than ultrasonic frequencies, and could be produced at higher intensities using available technology. The mechanism was simple but effective. Large pneumatic pistons driven by compressed air oscillated at precisely controlled frequencies, generating powerful infrasonic pressure waves. Parabolic reflectors focused these waves into directional beams. The apparatus was massive, requiring a platform the size of a small truck, but could theoretically produce acoustic intensities sufficient to cause internal injuries, disorientation, and potentially death at ranges exceeding 100 meters. The prototype that emerged in early 1915 looked nothing like a weapon. Wood's acoustic cannon resembled industrial machinery, a framework of steel supporting 4 large pneumatic cylinders arranged around a parabolic concrete reflector measuring 12 feet in diameter. Compressed air lines are fed from storage tanks mounted on a separate truck. Control systems regulate piston frequency and amplitude. The entire assembly weighed approximately 8 tons, making it immobile without significant logistical support. Initial tests at Toulon Naval Arsenal in March 1915 targeted laboratory animals, rats, rabbits, and eventually dogs. The results were dramatic and disturbing. Animals placed in the acoustic beam's focal zone exhibited immediate distress, disorientation, loss of coordination, and within 60 to 90 seconds, death. Autopsies revealed massive internal injuries, ruptured organs, internal bleeding, and tissue damage consistent with violent mechanical trauma. The cause was acoustic resonance. Infrasonic frequencies matched natural resonance frequencies of internal organs, causing them to vibrate destructively. French military observers were impressed but recognized immediate problems. The weapon required line of sight to targets, limiting effectiveness in trench warfare where soldiers were protected by earthworks. The acoustic beam, while focused, still spread with distance. Effectiveness declined beyond 50 meters, and most critically, the weapon was indiscriminate. Any living creature in the beam path suffered effects, including friendly forces, if positioning was imprecise. French artillery officers concluded the acoustic cannon was tactically impractical. The weapon's immobility, power requirements, and limited range made it unsuitable for frontline deployment. But the underlying technology demonstrated that sound could be weaponized, validating theoretical concepts that had seemed implausible years earlier. But Robert Wood's research had attracted attention elsewhere, in Germany, where parallel acoustic weapon development had progressed further. Professor Paul Langevin, a French physicist who would later pioneer sonar development, discovered through intelligence sources that German researchers at the University of Berlin had constructed acoustic weapons using Wood's published research as a foundation. German devices used piezoelectric transducers, crystals that converted electrical energy directly into mechanical vibration to generate ultrasonic frequencies at intensities exceeding Wood's infrasonic apparatus. The German approach sacrificed range for compactness. Their ultrasonic generators were portable, powered by field generators, and potentially deployable at the battalion level. Testing of German acoustic weapons revealed disturbing capabilities. At ranges under 20 meters, focused ultrasonic beams caused immediate incapacitation, severe pain, disorientation, nausea, and temporary blindness. Prolonged exposure, exceeding 30 seconds, caused permanent tissue damage, including hearing loss, internal hemorrhaging, and neurological effects. The weapons were silent to human ears, produced no visible effects, and left victims with injuries that contemporary medical knowledge couldn't explain. German military authorities tested acoustic weapons against live subjects, French and Russian prisoners of war during 1916. Records captured after World War II documented these experiments. Subjects exposed to focused ultrasonic beams exhibited symptoms ranging from severe discomfort to death, depending on exposure duration and intensity. The research violated international law regarding the treatment of prisoners, but German military leadership justified the experiments as necessary to develop weapons that might break Allied defensive positions. Despite apparent effectiveness in controlled testing, German acoustic weapons faced the same practical limitations that had doomed French development: inadequate range, high power requirements, and vulnerability to countermeasures. Soldiers could escape acoustic weapons by moving outside the beam path or behind solid cover. The weapons couldn't penetrate earthworks or fortifications, and their effectiveness declined dramatically in adverse weather. Wind, rain, and temperature gradients all disrupted acoustic propagation. By 1917, both Allied and German acoustic weapon programs had been abandoned in favor of more conventional technologies. Poison gas, despite international condemnation, proved more effective than acoustic weapons. Tanks, though mechanically unreliable, could cross trenches and break through defensive positions in ways acoustic weapons couldn't. Artillery, continuously refined through the war, delivered devastating firepower at ranges acoustic weapons couldn't approach. But the knowledge that sound could kill didn't disappear with the armistice. Post-war scientific conferences discussed acoustic weapon research openly. Robert Wood published detailed technical papers describing his infrasonic cannon, arguing that transparency would prevent future development by demonstrating the technology's limitations. Paul Langevin, transitioning from weapons research to developing underwater acoustic detection, what would become sonar, shared findings about ultrasonic propagation and focusing. The scientific community believed that acoustic weapon technology had been explored, found impractical, and would remain a historical curiosity. They were wrong. By the 1930s, as Europe rearmed and another war seemed inevitable, acoustic weapon research resumed quietly in Germany, Japan, and the Soviet Union. Nazi Germany, rebuilding military capabilities in violation of Versailles Treaty restrictions, pursued every theoretical weapons technology. The Luftwaffe, established secretly in the early 1930s, funded research into acoustic weapons for air defense. The concept was simple. Aircraft were vulnerable to acoustic damage because they contained sensitive equipment, thin-skinned fuselages, and human crews in confined spaces. An acoustic weapon that could disable aircraft without traditional anti-aircraft fire would bypass Germany's shortage of conventional air defense systems. Dr. Richard Woloschek, an Austrian physicist working under contract for the Luftwaffe through Lofer Company, developed a vortex cannon based on acoustic principles. The device used controlled explosions, acetylene and oxygen detonated in a combustion chamber, to generate powerful vortex rings traveling at supersonic velocities. These vortex rings carried tremendous kinetic energy, concentrated in a narrow region. At close range, within 50 meters, vortex rings could physically damage aircraft structures, shatter windows, and potentially injure crews through violent pressure changes. Testing at Hillersleben Proving Ground demonstrated limited effectiveness. The vortex cannon could damage stationary aircraft at close range, but couldn't track moving targets effectively. The weapon's firing rate, approximately one shot every 30 seconds due to reloading and cooling requirements, was inadequate for air defense, and vortex rings dissipated rapidly in atmospheric turbulence, limiting the effective range to approximately 100 meters. But Woloschek's research demonstrated a critical principle. Acoustic energy could be weaponized using chemical energy rather than electrical power. This made acoustic weapons potentially field deployable, eliminating the massive generators that had doomed earlier designs. German military authorities authorized continued development, hoping that engineering refinements would produce tactically viable weapons. Simultaneously, Japanese military researchers pursued acoustic weapon development with disturbing determination. The Imperial Japanese Navy, recognizing that American industrial capacity would eventually produce overwhelming naval superiority, sought technological advantages through unconventional weapons. In 1937, the Navy Technical Research Institute initiated Project Z, researching acoustic weapons for anti-ship and anti-aircraft applications. Japanese researchers discovered that focusing ultrasonic energy underwater produced more effective lethality than through air. Water transmits acoustic energy more efficiently, enabling higher intensities at greater ranges. Underwater acoustic weapons could potentially disable submarine crews, damage torpedo tubes, and disrupt electrical systems through cavitation, the formation and violent collapse of bubbles caused by intense pressure fluctuations. Prototypes tested in Yokosuka Harbor demonstrated proof of concept. Ultrasonic transducers powered by ship generators produced focused beams that killed fish at ranges exceeding 20 meters. Divers exposed to acoustic beams reported severe pain, disorientation, and lasting neurological effects. But scaling underwater acoustic weapons to tactically useful ranges, hundreds of meters against enemy submarines or ships, required power levels Japanese electrical technology couldn't achieve. Project Z continued through 1942, but produced no deployable weapons. Japanese researchers concluded that acoustic weapons, while theoretically effective, couldn't be manufactured with available resources. Japan redirected research toward conventional weapons that could be mass-produced, kamikaze aircraft, suicide torpedoes, and ultimately proposals for chemical and biological weapons. The strategic implications of acoustic weapon research extended beyond direct military applications. Scientists studying acoustic effects discovered that even non-lethal intensities could cause psychological effects. Infrasonic frequencies below 10 Hz, felt rather than heard, induced anxiety, disorientation, and fear in exposed subjects. Some frequencies caused resonance in human eyeballs, creating visual disturbances and hallucinations. Military researchers recognized potential applications for psychological warfare. Acoustic weapons that didn't kill, but rendered enemy forces' combat ineffective through terror and disorientation. But ethical concerns prevented widespread development. International humanitarian law, codified in the Geneva Conventions, restricted the use of weapons causing unnecessary suffering. Acoustic weapons that induced terror without permanent injury potentially violated these restrictions. More pragmatically, acoustic weapons faced the same tactical limitations that had prevented deployment in World War I: inadequate range, weather sensitivity, and vulnerability to simple countermeasures like hearing protection. By 1945, acoustic weapon research had produced extensive documentation but no operational weapons. American forces occupying Germany discovered complete records of Nazi acoustic weapons programs, technical specifications, testing results, and disturbing evidence of human experimentation. Japanese acoustic research documentation was seized during the occupation, revealing similar patterns of theoretical success and practical failure. Soviet forces captured German acoustic weapon prototypes and research facilities, initiating their own development programs that would continue through the Cold War. Post-war analysis by Allied technical intelligence teams concluded that acoustic weapons represented genuine physical phenomena, but were impractical for military deployment given available technology. The power requirements, limited range, and environmental sensitivity made acoustic weapons inferior to conventional alternatives. The research was classified, buried in military archives alongside other captured German weapons development, and largely forgotten. Except Robert Wood's original insight that sound could kill had been proven absolutely correct. The Mad Doctor, dismissed as a theatrical eccentric, had discovered a fundamental principle that dozens of researchers across multiple nations spent decades validating. Acoustic energy, properly focused and amplified, could cause lethal damage to living tissue. The technology wasn't science fiction or pseudoscience, it was physics, applied with lethal intent. But the same physics that made acoustic weapons possible also imposed limitations that prevented operational deployment. Sound energy is dispersed with distance following the inverse square law. Doubling the distance reduced intensity by 75%. Focusing acoustic beams required large reflectors or precise transducer arrays that were difficult to manufacture and fragile in field conditions. Atmospheric conditions, temperature gradients, humidity, wind, all degraded acoustic weapon performance unpredictably. Wood understood these limitations when he built his acoustic cannon in 1915. He never claimed the weapon was practical, only that it worked. His goal was to demonstrate that sound could be weaponized, hoping the demonstration would inform policy decisions about weapons development. Instead, his research inspired decades of efforts by less scrupulous researchers who ignored practical limitations in pursuit of invisible, silent weapons. The legacy of acoustic weapon research extends into contemporary military technology. Modern directed energy weapons include acoustic systems derived directly from World War I and World War II research. Long-range acoustic devices, LRADs, developed for crowd control and anti-piracy operations, use focused ultrasonic beams to cause pain and disorientation without permanent injury, exactly what Robert Wood's original research predicted. Active denial systems, using millimeter-wave radiation rather than sound, employ similar principles. Invisible, focused energy causing immediate discomfort that forces subjects to leave affected areas. But these modern systems incorporate safeguards and restrictions that their historical predecessors lacked. Contemporary acoustic weapons are designed specifically to be non-lethal, with automatic shutoffs preventing exposure sufficient to cause permanent damage. International humanitarian law now explicitly restricts directed energy weapons, requiring that they minimize permanent injury while achieving tactical objectives. The horrific human experimentation documented in Nazi and Japanese acoustic weapons research contributed directly to post-war international agreements prohibiting such practices. The scientists who pursued acoustic weapons faced ethical dilemmas that remain relevant. Robert Wood agonized about developing weapons, but concluded Allied victory required every possible technological advantage. Paul Langevin shifted from weapons research to sonar development, preferring defensive technologies to offensive ones. German and Japanese researchers, working under authoritarian regimes, conducted experiments that violated fundamental human rights. All grappled with the central question: does scientific knowledge justify its application to warfare? Wood's answer, articulated in writings after World War I, was that scientists bore responsibility for understanding potential applications of their research but couldn't prevent all misuse. He argued for transparency, publishing research openly so that countermeasures could be developed and policymakers could make informed decisions. The strategy partially succeeded. Acoustic weapon limitations became well understood, preventing unrealistic expectations and limiting resources devoted to impractical technologies. But transparency also enabled proliferation. Soviet acoustic weapon programs, continuing through the 1980s, built directly on captured German research and published Western scientific literature. Cold War rumors of Soviet psychotronic weapons, devices using electromagnetic and acoustic energy to manipulate human psychology, reflected genuine research programs pursuing Robert Wood's original discovery that acoustic energy affected living tissue. In university physics departments today, acoustic weapon research is taught as a historical footnote rather than serious military technology. Students learn that infrasonic frequencies can cause resonance in human organs, that ultrasonic waves can be focused like light, and that sufficient acoustic intensity causes tissue damage. The principles Robert Wood discovered in 1899 are now textbook physics, stripped of their connection to weapons development and human experimentation. What isn't taught is the human cost of that knowledge. The prisoners exposed to German ultrasonic weapons suffered permanent hearing loss and neurological damage. The laboratory animals were killed by the thousands in tests conducted by Allied, German, and Japanese researchers. The scientists who devoted their careers to developing technologies that never achieved military usefulness but left detailed documentation of how sound can be used to kill. The mad doctor who turned sound into a weapon wasn't mad. Robert Wood was a brilliant physicist who recognized that acoustic energy obeyed the same physical laws as light and electricity, and that sufficiently intense acoustic waves would damage tissue just as intense light burned or intense electricity shocked. His crime wasn't discovering these principles; they would have been discovered eventually regardless, but demonstrating them so convincingly that military establishments across the world invested decades pursuing weaponization. Wood died in 1955, his acoustic weapons research a minor footnote in a career spanning 5 decades of groundbreaking physics. His obituaries focused on contributions to spectroscopy, optics, and photography. The acoustic cannon built in Toulon was barely mentioned, dismissed as wartime desperation rather than serious scientific work. But the technology Wood pioneered lived on, refined through decades of research into directed energy weapons, acoustic crowd control systems, and ultimately the non-lethal weapons deployed by modern military and law enforcement. The sonic weapon that killed 17 rats in 90 seconds in 1915 established proof of concept that shaped weapons development for the next century. The principle that sound could be weaponized once proven couldn't be disproven. Every subsequent researcher knew that acoustic weapons were physically possible. The question was only whether they were practically useful. The answer, that acoustic weapons had limited applications but could achieve specific tactical objectives, emerged slowly through decades of research that Wood's initial demonstration had made inevitable. The lasting lesson isn't about acoustic physics or weapons technology. It's about the relationship between scientific knowledge and military application. Every fundamental discovery in physics, chemistry, and biology is evaluated for weapons potential. Scientists who make discoveries bear some responsibility for foreseeable applications, but can't prevent all misuse. The balance between pursuing knowledge and preventing harm remains unresolved, contested by each generation of researchers who must decide what to study and what to publish. Robert Wood chose transparency, believing that understanding acoustic weapon limitations would prevent wasteful development and unrealistic expectations. His choice succeeded partially. Acoustic weapons never achieved the strategic importance their proponents predicted. But transparency also enabled continued research, some of it conducted unethically, pursuing technologies that Wood himself acknowledged were impractical. 84 years after Wood's acoustic cannon demonstration, his principle remains valid. Sound, properly amplified and focused, can kill. Modern acoustic weapons incorporate technologies Wood never imagined: piezoelectric transducers, phased arrays, computer-controlled focusing, but operate on principles he discovered. The mad doctor's sonic weapon, dismissed as theatrical pseudoscience, proved to be accurate physics ahead of available engineering. The technology eventually caught up to the theory, producing exactly the limited utility weapons Wood's research predicted. The apparatus that hummed below human hearing in Toulon Naval Arsenal sits nowhere today, dismantled decades ago and lost to history. But the knowledge it demonstrated, that invisible acoustic energy could cause lethal damage, persists in military research programs, international humanitarian law discussions, and university physics courses teaching wave mechanics. Sometimes the mad doctor is right even when everyone hopes he's wrong. Sometimes the science fiction weapon works, just not well enough to matter. And sometimes the terrible knowledge can't be unknown, no matter how much we wish it could.